Matteo. Thanks a lot, Christian. Thank you, everybody, for being here. It's a pleasure to be in Lugano and present my ongoing work. As you can see, it's sort of a mixture of metaphysics and quantum mechanics and physics. The reason I decided to present this is that I take it as a paradigmatic example, something that I really think should be appreciated, namely that the relationship between metaphysics and science is not as straightforward as many people seem to think nowadays. As I will try to show, even if you're a naturalist, not just by looking at the evidence coming from science that we can learn metaphysical lessons. It is actually much more complicated than that. So I'm not going to conclude with a positive claim. So this is the way things are. My main aim is to do the opposite in a way. We don't know the way things are. Things are complex, and if we put metaphysics and science together, we get a huge number of alternatives. And the main task, I see, from the physician of science should be to actually see all the alternatives without thinking that, if you're a naturalist, you can actually learn from science. Okay, so some background first. Take this rock, for example. Let's suppose that this piece of stone is an individual. Let's define individuality. Let's say that object X, like this stone, is an individual if and only if X is determinately self-identical and numerically distinct from every other entity at a given time. As you will see, this is not trivial at all. Then, of course, an individual could be identified as the same thing at different times. But this is not crucial, because if only because an individual could be an instantaneous individual. Something exists for an instant, it is an individual, and then that's it. So we will focus on these synchronic identity conditions. So what follows from this is the following. Given a plurality of individuals, then you have two facts about them. They are cardinally countable, namely it is determinate how many they are, and they are also ordinally countable. They can be labeled. We can say this is one, this is another one. These are two very different things, so we need to have both to have individual. So I'm assuming, then we can discuss it later, that individuality is an intrinsic feature of things. It's not like first you get a bunch of things and they exist together and then you have individuality. Individuality is a fundamental feature of existence. Okay, now the obvious question is, okay, what is the contrast class? Everything is an individual, right? As you characterize the concept, it looks like everything is an individual. This is not the case. The first difference is between individuals and objects which are relationally or structurally determined. So the identity conditions in this case are extrinsic. They are not intrinsic to objects. Most importantly, the main contrast class we will be interested in is this, objects without self-identity. Objects that we know how many they are, but they are not ordinarily countable. Think about usual examples, money units in a bank account. I know that I have 1,000 euros in my bank account, but if you ask me which one is which, it makes no sense, right? Same thing for this jug of water. Say you have a glass and you put 5 glasses of water in the jug. There's no point in asking which glass is which in the jug, okay? So obviously this is an analogy, but in quantum mechanics, this is an important analogy because this is what non-individuality is taken to amount to in the case of quantum particles. So many philosophers nowadays, they claim that quantum particles are like units of water in the jug. Sounds funny, but this is the established view. But before discussing that, let me say a few things about trans-world identity facts. So individuality is about intra-world identity facts. Given a world, you have individuals, or maybe you have something else. But we also need to ask something about identity conditions across world. Identity conditions which are relevant for model facts. And simplifying a little bit, we have mainly two options here. Haecceitism, defended here by Robert Adams, whom maybe you know. He thought that individuals have primitive businesses, and this makes Haecceitism the case. Haecceitism is basically the view that two distinct worlds, namely two possible arrangements of objects and properties, may differ merely with respect to which object is which. This is called an haecceitistic difference, and it means that you may have two or more indiscernible universes, which are exactly similar, but still they differ because there is a difference in which object is which. A purely haecceitistic difference. Other philosophers like Graham Forbes here, they reject haecceitism. They endorse anti-haecceitism, which is obviously the view that any two distinct possible worlds, they differ at least with respect to some qualitative fact. So there are no haecceitistic differences. This is the contrast that we'll be interested in. Before I continue, one important remark. Haecceitism being the case is not the same as things possessing haecceities. Maybe this sounds obvious, maybe not, so let me make it clear. What is an haecceity? An haecceity is something that was posited for the first time explicitly by Scotus here in the Middle Ages. It is supposed to be a purely metaphysical factor determining the singularity of every specific substance, right? So you have a bunch of qualities, substances exemplifying these qualities, but what makes each individual that thing is an haecceity. Or primitive business. This is a terminology by Robert Adams. Now, haecceitism is obviously naturally explained if things have haecceities, right? Because if things have haecceities, then it is at least possible for two identical, exactly similar things to be this thing and this other thing, okay? But it is important to understand that haecceitism does not reduce to this. So haecceitism and the possession of haecceities are logically independent, okay? We'll get back to this, but this is basically just terminology. So now, given this background, what happens in physics that draws our attention? As a warm-up, let me start with space-time points. General relativity. Of course, we need to look at general relativity if you want to know how space-time behaves. Now, there is, of course, a long-standing debate in philosophy about the ontological status of space and time. And this debate continues in general relativity. What is space-time? Is it a substance, a system of relations, a system of structural connections? Now, suppose, just for the sake of argument, that space-time is a substance. This means that you have a substance which is constituted by points, which are substantial, of course. Now, we may think that if space-time points are substances and they have intrinsic identities, then haecceitism has to hold, right? Because this point and this point, they are two distinct individuals. And if I switch them, I have to have a new arrangement. Now, this is supposed to be problematic. Maybe you are familiar with the old argument. If you are not, the idea is basically, very roughly, that if you have that model on the left, this is a possible description of space-time, right? But if the space-time points are individuals, it is possible, it has to be possible to switch them with one another. And one particular switching is the one represented on the right. You only switch the identities of the points within a region, and this has very important consequences. The consequence that we are interested in is that the description on the left, in which material object E crosses a region, is different from the other one. The material point E does not go through the hole, okay? So why is this problematic? Basically, because we have two different descriptions of the same, or what seems to be the same thing doing the same motion, but there is no fact of the matter as to whether E passes through the region, the hole, right? And this is problematic because it looks like general relativity, which is not a deterministic theory, now becomes indeterministic, right? Given what we know about E, we cannot tell whether at the next instant it will be in the region or not. Why? Because either one of the two models could be the right representation. So I'm not going to discuss this in detail. What's the usual reaction to this? It is this: space-time points are permutation invariant. It makes no physical difference to switch them, right? Even if we assume that they're individuals, switching them with one another, just exchanging the labels, does not really describe a new situation. So Haecceitism seems to fail. And the popular answer is that this happens because space-time points do not have intrinsic identity, okay? The identity of the points is merely determined by the set of metric relations in the whole of space-time. Why is this relevant for us? Because this entails that ordinal countability fails. We cannot label the points, right? Because if we could switch them. We cannot switch them, so they don't have labels. So they don't have identities. Of course, we can label something in space-time, but we merely label places in a space-time structure, not the points. So the conclusion is that space-time points are not individual entities. Of course, we can discuss it, but this is just a starting point. What is important for me is that you appreciate this line of reasoning. You start from a fact, so suppose the empirical fact of permutation invariant. We know that permutation invariance means that there are no Haecceitistic differences, and then we reason counterfactually. If the relevant entities possessed intrinsic identities, then we would see Haecceitistic differences. We don't see Haecceitistic differences, and therefore they are not individuals. Are you with me so far? Okay. So keep this in mind, from empirical fact of permutation invariance to a metaphysical conclusion. Then, of course, we can ask, what is a space-time point? This is not our problem today. Rather, let me switch to quantum mechanics, non-relativistic quantum mechanics. I will keep things simple because all the relevant facts are here. Now, we have a similar debate in quantum mechanics, and the debate is a debate about the ontological status of quantum particles. Are they individuals? Are they not individuals? Why? There are, in fact, two arguments in favor of what is now called the received view. The traditional conception of quantum particles is that they are non-individuals. It's not really clear what it means to be a non-individual, but of course, it's something that fails the test for individuality. Two arguments are, maybe you already know that. One has to do with the Leibnizian principle of the identity of indiscernibles, which is violated, at least in its traditional variety, by quantum particles. But I'm going to focus on a different argument, which has to do with quantum statistics and the behavior of many particle systems of identical particles. Why is this? Well, first reason is that this argument is comparatively less discussed in the literature. There's been a lot of ink spilled on Leibniz, identity indiscernibles, and weak discernibility and all that. But historically, and I think conceptually, what it really does the heavy work of pushing towards non-individuality in quantum mechanics is actually quantum statistics. And of course, I'm going to focus on this today because quantum statistics, as we will see, is supposed to be directly connected to issues of Haecceitism versus anti-Haecceitism. So, as I said, I'm not going to say this is what quantum particles are. I want to do, my aim is much more modest. I want to see what the argument actually is, because there is an argument in the literature, but people actually refer to it without actually expressing the argument. And I think it is really important for our acquisition of time to actually slow down and see all the premises that are used to reach a conclusion. And if you really reach the conclusion after you consider all the premises. So what I will do is to formulate the argument and then see ways of trying to resist it. Not because I want to resist it, but because I want to see whether I can sharpen the argument. Then, in the end, but I will leave this important question in the background, we will see that the argument can be resisted. It can be formulated in many ways. There are many metaphysical alternatives. And this becomes a pressing question. There is no straight path from science to metaphysics. So I need to know how to go about choosing my metaphysics given the empirical evidence. But I won't say anything about that. Okay, again, crash course in quantum mechanics. Quantum particles of the same type, physicists talk about identical particles, but they're not identical in the logical sense. They are exactly similar. They share all their state-independent properties. So if you are a quark, then you will be that particular kind of thing. So elementary particles, they share their mass, well, relativistic mass, they share charge, they share the absolute value of spin. These things are there, they don't change. But then we have state-dependent properties. The contrast is a little bit, state-independent properties are essential properties. If you're a boson, if you're a gluon, you have those properties. State-dependent properties are different because they are sort of accidental properties. They depend on the situation in which you find the particles. And now quantum statistics becomes relevant because if you have a bunch of particles, they can give rise to different combinations, and quantum statistics describes these possible arrangements of particles and their state-dependent properties. So, for example, what is an accidental property? The specific value of spin of one particular particle along a specific direction. So that particular particle, not the kind. Okay? Now, I will stick to a very simple, very naive scenario because it's sufficient for my purposes. Now, consider two systems. We will call them 1 and 2. But it's arbitrary. I'm not labeling them. I'm just telling you there are two. Two systems and two possible states. Now, the classical setting, which exemplifies this, is, of course, a two-coin system. You toss a coin, and then you toss another coin, and you count the combinations. Now, of course, if the coins are fair, it is easy to see that the available arrangements are 4. I'm using vector notation here just for fun. You can have one coin heads and the other coin heads, two coin tails, the first coin heads and the second tails, and the first coin tails and the second heads. This is obvious. What is less obvious? Well, we need to pay attention to the last two states, right? There are 4 possible states, and they are equally probable. So the last two states, they have 25% probability of occurring, okay? Why focus on the last two? Because the last two in this toy model exhibit haecceitistic differences, right? Because we switch coin 1 and coin 2, and everything else remains unchanged, okay? So just to be clear, forget about position. Of course, we know that this coin here is here and the other one is there. But this is not in the model, okay? So in the model, we have an Haecceitistic difference. So classically, this is fine. This means that coins are individuals, okay? Now, something funny happens in quantum mechanics, because now replace coins with quantum particles, replace heads and tails with spin up and down along a particular axis, and you get 3 states. They are, again, equally probable given certain assumptions. But I had 4 states, now I have 3 states. The first 2 states are superficially at least the same states. But the last 2, they become 1. And this is a typical quantum state in which we know that one of them is up and the other one is down. It's not like we don't know which one. We cannot tell. There is no fact about one being spin up. So this is the important thing. All the 3 states, all the possible states in the quantum case, they are symmetrical. The so-called symmetrization postulate holds. Quantum identical particles in the same state can only be in symmetric states. What does this mean? States in which exchanging the particles does not make a physical difference. Again, let me stress this, if you're not familiar with quantum mechanics. The last state is a state which is entirely symmetric. It tells us that one particle has or will have spin opposite to the other. The spin is opposite. It's not like we already know the value, okay? So as Bose tells us, we need to be more precise. There are different particles, different families of particles. Bosons, which are force carriers, they can only be in symmetric states. So the first 2 and the last one with the plus sign in the middle. Fermions, they can only be in anti-symmetric states. So only the last state with a minus sign. This is just for being precise, but this is not relevant. What is relevant is that whatever particles you want to describe, if they are particles of the same type, they will find themselves in these states, and only this, namely symmetric states. And that's why physicists introduce this definition. Identical particles in the same state, they obey the indistinguishability postulate, which is basically to say that they are permutation invariant. If you switch one particle with the other, you don't get physically a new state. So you can appreciate the difference with the classical case, right? You switch the coins, you get a new state, and the probabilities are changed accordingly. In this case, you have the same probability, 1/3, 1/3, and 1/3. And the last state weighs the same as the first 2. Why? Because switching the particles does not change it. It's the same state. So what is the analogy with the space-time case? In this case, too, the evidence has led many philosophers to think that the entities we are describing, they are not really endowed with intrinsic identities. They are not individuals, right? They are something different. There is a famous quotation by Hermann Weyl. Some of you probably know it. This is what he said, I think it was 1928, so 1 century ago. The possibility that one of 2 individuals, Hans and Karl, is in the quantum state E1 and the other is in the quantum state E2 does not encompass 2 discernible cases, which arise by permuting Hans and Karl. It is impossible for either of these individuals, Hans and Karl, who have the same nature, to retain his identity. Even in principle, one cannot demand an alibi of an electron. So, of course, he says individuals, but he uses in a very sloppy, unphilosophical fashion. He means an entity, a thing, okay? An object. But he's pointing towards a very important evidence, right? Even if you give names to particles, then you cannot switch them with one another and expect the name to carry over, because it's not a new situation. And this is why the received view became popular already in the 1930s. Why is this the case? They are permutation invariant. Why? Usual answer is this. It is because they don't have self-identity. They are non-individual. So we can count them, but we cannot really tell this is one and this is the other, like the glasses of water in the jar. So again, the structure of the argument seems to be exactly the same, right? We observe permutation invariance, we have this counterfactual step, and then we end up saying that these things, whatever they are not individuals. Now, again, to be clear, I'm not going to say that this is false or wrong. My main aim is to actually see the argument more closely and actually discuss with you guys whether all the assumptions are compelling. Then in the end, if time permitting, I will have some slightly original suggestion to make, but that's an independent aim. So the next step is going to be to make the argument a little bit more explicit. So this is the way I thought it could be reconstructed. So first assumption, first premise, we assume that particles are individuals, just to see what happens. Given the definition of individuality, this means that they have determinate intrinsic identity. Two follows from one. Then we call the empirical evidence into play, and we see that identical particles in the physicist set, exactly similar particles, particles of the same family, when they are in the same system, they are indistinguishable. They are permutation invariant. They only give rise to symmetric states. But then, if you have exactly similar things in the same state and they are individuals, then you should be able to switch them. Are you with me on this? I'm assuming in the quantum case, it's important that there are at least two, okay? They are exactly in the same state. So if you have two exactly similar things and they're individuals, you should be able to switch them. So we get to premise 4. Particles may or maybe should give rise to excitistic difference. However, now we have the evidence that they don't, so we get a contradiction, right? The obvious suggestion is to just drop one. All the rest is evidence, right? So by reductio, it looks like the CQ is really the only way to go. So it might be, but in the next 20 minutes or so, I'm going to argue that it's not so simple. So one possible defense could be this. Well, look, the argument is not valid because that X is not the case does not entail that X cannot be the case. Just for clarity, let me remind you of premise 4 and premise 5. Now you see the problem. Now I highlighted it. Particles may give rise to excitistic differences if they are individuals. What we see is that they don't. It's a big step, right? Now, in my reconstruction of the literature, I think some of the attempts that you can find in the philosophy physics literature go exactly in this direction. What I mean by this? The idea is that basically, if you want to defend the idea that quantum particles are individuals, you might want to provide an explanation as to why, even though excitistic differences should be possible, that they are not actually the case in this world. One option could be, as Stephen French said at some point, like 40 years ago, well, look, they are individuals. Potentially, they could give rise to excitistic differences, but they don't. This is just the way this world is, contingently. There are some state accessibility restrictions. So only symmetric states are allowed, and this is why you can switch whatever you want, and you don't get a new state. Now, we could discuss this, but I don't think it's really promising, because it really tells us, it gives a name to the problem, right? We want to explain why we don't have excitistic differences. And just saying that there are restrictions on the accessible state is sort of question begging, right? Anyway, I will assume that it is. Another option is to do something more daring, which is to give up on the fundamental postulate of statistical mechanics. What does it mean? Basically, give up on equiprobability. So usually we used to assume the principle of indifference. If we have a bunch of possibilities, we don't know anything about them, we give the same weight to all of them. This works in a lot of cases, but it's not that straightforward. So the idea could be, well, look, maybe in quantum mechanics, what really needs to be rediscussed is this idea that all the states are equally probable. These two physicists actually suggested this like 50 years ago, but wasn't really pursued. Now, this is promising, more promising. So what is the idea? Let me again provide you with an example. When you have the two bosons we met a moment ago, you have these three states. I mean, this is the usual description, right? Usual description is that you have three equally probable states, 1/3, 1/3, 1/3. What's the solution? It's obvious, right? If you're allowed to change probabilities, you would write this. You actually have four probabilities, four possible cases, right? Why these ones? The classical ones, because they are individuals and they have to be as close as possible to classical individuals. So we pick the states and then we give the appropriate weights, right? So if you think about it, this is empirically equivalent to that, right? Whenever you don't have two spin up or two spin down, you have one of these two. You don't know which one, but it doesn't matter. Okay, I don't know about you guys, but I'm not convinced, because usually if you want to drop equiprobability, and in this case, if you want to drop the fundamental postulate of statistical mechanics, you need to have a very good physical reason. In this case, you don't seem to have a very good reason at all. I mean, the reason is basically that you want to think of your particles as individuals. And only because you want that, then you will actually compute the probabilities that give you the right result. Now, this is not entirely problematic per se. The problematic aspect is that in this case, we make an assumption which is not empirically supported at all. Because think again about this scenario and the other one. There is no way of distinguishing between the two. Okay, so we are assuming that the probabilities are different in this particular way, and yet, if we look at things, they seem to behave in the other way. So basically, the problem is that we make an assumption at the level of statistics, which is not supported by direct empirical evidence. Okay. Some people may think that this is too high a cost. You need to have a more compelling empirical support. And additionally, people like Van Frassen suggested that if you really look at the whole architecture of quantum statistics, going this route does not really allow you to save all the results. So the idea is basically, but this is something we cannot discuss here, is that the proposal is actually empirically inadequate. Because when you move away from these two examples, then there are cases which cannot be explained by simply dropping the fundamental postulate. Okay? Now, so this suggestion is not really promising, but still, we have a lesson to learn. And the lesson to learn is that in the argument for non-individuality, we need to make explicit our assumptions about the specific way in which the statistical behavior is to be described. Okay, but we will get back to this. Second reply. Let's see if it is more promising. Now, second reply could be this. The argument is invalid because that a bunch of things are indiscernible individuals at the intra-world level does not entail Haecceitism with respect to trans-world identity. Remember what I said a moment ago. having an anxiety, being an individual, having intrinsic identity is a fact about this world. Model facts are different, and there is no immediate implication between the first class of fact and the second class. So let me spell this out in this case. For simplicity, let me again remind you of the premises. Now, this part of the argument becomes relevant. We start with individuality, then we assume the fact of permutation symmetry, and then we infer that particles may give rise to, should give rise to haecceitistic differences. Now, the reply is basically that the move, from 2 and 3 to 4 is not obvious. Why is this? Because there might be ways of exploiting this gap between intra-world identity conditions and trans-world identity conditions, stopping the conclusion from being drawn. Now, one option in this sense is counterpart theory. Well, so it seems to me. There would be a lot to say about counterpart theory because it's complicated in itself and could be applied in many different ways, but I'll try to stick to the basics. Now, what is the idea? Maybe you already know this. On a counterpart theoretic account of modality, we really don't have trans-world identities. It's not like I am identical to the me who is not doing a talk in Lugano. Really, we have counterparts, and counterparts are defined on the basis of similarity relations, okay? So if we weaken identity so as to make it a similarity relation, then there are ways out of the argument, or so it seems. The basic idea is this. If you are given two indistinguishable particles, 1 and 2 in this world, they are in the same symmetric or antisymmetric state in the actual world. Any world W, which differs merely in terms of a switching of labels, switching of one particle with the other, does not, in fact, differ at all from the actual world, okay? It is exactly similar. So it is not a different possibility. It is the same thing, okay? So the idea seems to be if you, by counterpart theory, you can stick to individuality and say that individuals actually cannot just change labels, right? So it's just a matter of labeling. If you call one of them 1, the other one will be 2, but this is not a metaphysical fact. It's just putting some labels. You could switch the labels, but you're not switching the individuals. So let me be clear on this. I don't think it's a compelling argument, but the argument has to be clear. The argument based on counterpart theory is basically this. In the classical case, you have this haecceitistic difference, and it is okay, because from a counterpart theoretic viewpoint, there is a difference between this and this, right? Because you are switching two things in non-symmetric state. I hope you appreciate this. This is not identical qualitatively with respect to the other one. In the quantum case, switching does not make any difference in terms of similarity, okay? So the idea is basically that if you have anything like this, a truly completely symmetric state, then counterpart theory doesn't count the two combinations as two different possibilities, okay? So you have one and only one world. Now, of course, we can discuss this more deeply later. Let me just move on. I think this is not compelling. And my argument for this, I hope you will appreciate it. I cannot be too long on this. I want to express my doubts by going back to space-time points for a moment. It seems to me that in the space-time case, this is a good strategy. Because basically, if you think about space-time points, from a qualitative point of view, what is relevant is the set of metric relations, right? You take space-time as a whole, the distribution of matter in space-time. Once you've given that, then you have a bunch of places in the structure, and each one of the places is unique. So counterpart theory works now because each place is a space-time point. If you switch the points, it doesn't change anything because the same place will be that point, okay? Now, I want to suggest that this is not what happens in the quantum case. Paul Teller said something like this a long time ago. I want to make it more explicit, or I mean, like, maybe I'm saying the same thing. But anyway, what is the difference? Remember what I just said. Space-time points are qualitatively unique. Quantum particles are not, because the whole point is to have two or more exactly similar particles in the same state. So basically, counterpart theory becomes useless now, because I have two things, and I cannot simply say that world in which I switch the labels is the same. Why is this? I will ask David Lewis for help. He said something which I think is pretty relevant in these articles, cheap Haecceitism. I'm not saying that the proposal is correct. I'm saying he has the right intuition. He says something which is really relevant, I think. He denies the idea that we should count distinct possibilities by counting the worlds. Why is this? Because he says, be careful, a single world may provide many possibilities, since many possible individuals inhabit the world. This is the classic twin example. I might have been one of a pair of twins. I might have been the firstborn one or the second-born one. So I think this carries over to the quantum case. Even if you're a counterpart theorist, you still have to explain which particle plays which role inside one world. Okay? I hope you're with me. Counterpart theory is really connected to qualitative roles, right? In the space-time case, it is easy because there is only one role each point can play. In the quantum case, this is not the case. Every couple of identical particles in the same state is like a couple of twins. And it does make sense to ask whether I could be the other, okay? And counterpart theory, and I think that Lewis is right, cannot ignore this fact. It is a sensible question, okay? So again, this is not really promising, but it is useful for us because now we know that whatever argument we're going to have in the end, if you want a compelling argument for non-individuality in the quantum case, you need to make your model philosophy explicit. And we will get back to that. How am I doing on time?
70 minutes.
Okay, third reply. Another defense could be this. Look, the argument is invalid because quantum statistics is about properties, and the argument doesn't say anything about properties. Again, let me make this explicit by going back to the premises. Premise 2 is familiar. If we assume particles to be individuals, they have to have intrinsic identity. But we know that we can have exactly similar particles in the same state, and in that case, we will have permutation symmetry. And this means that particles may give rise to Haecceitistic differences. Now, it seems to me that there is a gap here. If you have individuals, what is switched when you actually do quantum statistics? Properties. So I think we need to make something explicit, which might be obvious, but it's not that obvious. Particles need to possess properties as their monadic properties, right? Otherwise, switching does not necessarily lead you to a new scenario. So let me make this more explicit. It seems right to add that premise, right? Because it is only if and only if, say, A has its monadic property, say, being heads, and the same holds for B, monadic property of being tails, that I can even conceive of the possibility of them exchanging the properties, right? In other terms, Haecceitistic differences between two objects can only be relevant if the objects have something to exchange. So we are not really exchanging identities, we are exchanging properties. This is what quantum statistics does. Is this clear? Okay. So now we discovered that there is one hidden premise that we need to make explicit. And of course, one possible strategy could be for the defender of individuality to reject this hidden premise. And this premise can be rejected in several ways. Some of them are less promising than others. One option could be to go monist, okay? Well, look, particles don't have properties. They are just epiphenomena. They are derivative of the composite system. We have an object there, and it's A, B, the whole thing. And of course, A and B, they don't have any properties to switch. There's nothing monadic about A and B, because A and B are not even objects. Or you might go structuralist and say, well, look, quantum entities, they don't have monadic properties. They have only structural, namely relational properties to them. And of course, if you have two things and they are into a relation, switching them doesn't give you a new relation. It's the same relation. Especially because these relations, as we've seen, they are symmetric. Okay? I hope this is clear. If you have two people of the same height, saying that A is the same height as B, and then switching them and saying that B is the same height as A, doesn't describe a new situation, of course. Now, this might sound promising, but it's not, unfortunately, because it should be obvious. If you are a monist, you really don't care about quantum particles, and you really don't think they are individuals. Maybe the whole system is an individual, which is fine, but the question is whether the particles are individuals, and they are not. They are just potential parts of a whole. And of course, maybe you know that, if you're a structuralist, your main motivation is to drop the idea that quantum particles are individuals. So going structuralist is not really promising, because structuralists are actually keen to reject individuality. And they call relations into play exactly to conclude that identity is not intrinsic. Then I have a question. I mean, why should they be worried about the lack of discernibility as much as they are? But this is an independent issue. Anyway, so again, this third reply is actually useful, because now we see that we need to make something more explicit for the argument to work. What is this? Properties have to be monadic properties. But it's not all, and we get to what I take to be the neglected option that I want to put on the table. Again, I'm not going to say that this is the right way to go. I'm just saying that it's a potential alternative that was neglected so far because, in my diagnosis, because people didn't really spend time in making the argument explicit. So what is this option? I'll get to that. Again, let me go back to the premises. Now this is familiar. Individuality, intrinsic identity, monadic properties. Now we are assuming, we are conceding that properties are monadic. And then we have the empirical facts and the conclusion about haecceitistic differences. Now, again, it seems to me that we still need something else to get to the conclusion. What is this something else? Assumption 2B. We need three things. We need individuals, we need monadic properties, and we need all the combinations to be allowed. The way I put it there, the arrangements are arrangements of individuals and monadic properties without restriction. This has to be made explicit. Otherwise, why should we be sure that we should have haecceitistic difference? You see the point. Having an haecceitistic difference means that you have individuals, they are exactly similar, they have monadic properties, and they are allowed to exchange their properties whatever way they want, okay? If they are not, if there are restrictions, then the statistical output obviously changes. Okay, so this has to be made explicit. Now, the question is, why should I question 2b? 2b seems to be compelling. No, I don't think it's so compelling. It is regarded as intuitive by an entire school of metaphysicians, which are basically what I call the Hume, Armstrong, Lewis school, which is basically the Halt school, which is the view of physical reality, of reality as based on these two things. Humean supervenience. The whole of reality is a vast mosaic of local matters of fact, meaning objects in specific regions and their monadic properties. And there is this other component. Armstrong and Lewis, they insist a lot on this principle. Whatever exists cannot be modally constrained. Recombinability. Okay? You get a bunch of existence, you get your mosaic, all the combinations of the little pieces of the mosaic are allowed. Okay? Now, of course, if you believe this, then you believe in 2b and you believe in the argument. Okay? But is this really the only way to go? Of course not. If you do this in the quantum case, then now you're doomed. If you are a supporter of individuality, particles and their monadic properties, plus this sort of a particularist approach to metaphysics gives you Haecceitistic differences. There is no way out. However, my modest suggestion is that there are alternatives, right? Of course, Armstrong, Lewis, Hume, they are really important and authoritative, but there are different approaches. So let me put it like this. Maybe what we should learn from quantum mechanics is that really the Humean approach is wrong. It is not the case that things are really free to recombine whatever they, whatever way they want. One way of making this explicit would be to introduce in our metaphysics some constraints. So what is known as metaphysical coherentism, for example, is exactly this view. You may have a bunch of local things with their monadic properties, but importantly, the way in which they get together and they recombine, it is not completely free. It is actually strongly constrained by dependence relations. So in general, let me leave it the generic level. So if you have two things, and they are individual objects, and they have monadic properties, but they depend on each other in some ways, then it is not obvious that any combination is allowed. It depends on the constraint, right? So in general, metaphysical coherentism is the view that things depend on each other. They may depend on each other in different ways, either rigidly or generically. We don't need to get into the details here. In different respects, for their identity conditions, for their qualitative properties, even for their existence. It could be that, unlike what Hume thought, really reality is like this. This existent and this existent, they can only exist together. Why not? Okay, this is very generic. What would be the case in quantum mechanics would be something like that. If you have, again, consider the singlet state of two fermions and two possible states there. Now, a possible coherentist interpretation would be this. Look, they are individual objects. They have monadic properties. And I would think that they are probably going to be dispositions or indeterminate properties, because we don't know which value of spin one has, but this is not relevant. Then we know something else. The two particle system is such that the total spin has to be zero. We know that. It's a law of nature. Pauli's exclusion principle tells us that, okay, we don't know. They don't have definite spin, but they have to have one the opposite of the other. So what does this tell us? It tells us that there is a conditional nomological necessity. If they interact and they become entangled, they enter into a single state. And then there is a necessity for them to have a spin opposite with respect to the other. What is this, if not ontological dependence? It's a failure of free recombinability, right? I'm not saying this is obviously the case. I'm saying that it's a pretty natural reading, right? If they interact, something happens. They become dependent on each other, right? And if they become dependent on each other, then Hume is wrong. The Humean metaphysics does not apply. I know there is a lot of literature trying to defend Humean supervenience against this, but I think it's really weak. I think there is no point, if not just by saying, well, look, I really like that, and it has to be true. So the general idea is this. Maybe quantum mechanics is telling us that quantum statistics is unlike classical statistics because it describes systems which are mutually dependent in ways in which classical things are not. Okay, so by way of conclusion, first task was to reconstruct the argument. And I hope it's clearer now, maybe not by reading this, but this is what we got to by making all the objections explicit. Again, we assume individuals, then we assume that particles have monadic properties, then we assume the Humean approach to metaphysics, and then, only then, the evidence leads us to a contradiction and we have to drop individuality. So first conclusion is that if we really want to insist on non-individuality, then we need to go this route. We need to make explicit that it's not just the evidence that counts. It's the evidence plus a bunch of assumptions which are purely philosophical. And the second conclusion is that exactly because of this, now we have different ways of applying the reduction, right? Given the contradiction, we all agree that contradictions are bad. But now we have an alternative. We might drop one, but we could also drop 2b and go coherentist. And if you're a coherentist, you say, well, quantum statistics is not telling us that quantum particles are not individuals. It's telling us that they are individuals of a specific kind, namely mutually dependent individuals. Okay? But again, I'm just saying this is an option. Okay? So, very quick summary. We started by defining the identity condition, individuality, Haecceitism, and anti-Haecceitism. Then we looked at permutation invariance in physics. Space-time case, we didn't really discuss it in detail. We can discuss it now if you want. And the case of quantum identical particles. In the quantum case, which was my focus, I started by noticing that there is a received view to the effect that quantum particles are not individual. One of them has to do with the identity of indiscernibles. We didn't discuss it here. The other one has to do with quantum statistics and Haecceitism. And what I tried to do is to move from a very generic and sloppy formulation of the intuition to a more precise formulation of the argument. And this I take to be useful, at least potentially. And then I added something. Once we make these assumptions explicit, then we see that maybe there is a neglected way of solving the problem, and which is basically to drop out of a bunch of implicit assumptions that are often made in the literature about Humean particularism, about generalism, this idea that every relevant scientific fact has to be qualitative. This is really widespread, but I don't see any argument for it, but we can discuss it later. If we are not convinced, then we can at least conceive of an alternative along the route of coherentism. But again, I'm not saying this is right. I'm saying at least let's ask ourselves the question: what is worse? We should drop self-identity as the Humean route suggests, or maybe we can stick to self-identity and go for mutual ontological dependence. How should we decide? So this is a very pressing question. Now, of course, this is really important, and I'm just mentioning it. The point is, if we do, even if it's naturalistic metaphysics, if we do it properly, we see that there is no direct route from science to a metaphysical conclusion. And if we realize that, we see that metaphysics remains underdetermined. And if it is, we need to provide non-empirical criteria of theory choice. And this is a big if we will ever find this criteria. But of course, each one of us, if we try to do this, we need to provide criteria. If I prefer this to that, I need to explain why. If he prefers the Jungian approach, he has to tell us why. And this means that there is no algorithm from science to metaphysics. Okay, that's it. Thanks a lot.
You ask your second, other question, look at third. I'm gonna type your number. One question? Okay, let's start with one.
Thank you. This was really interesting. I have a question relating to some of the objections about sort of the danger of primitive non-identity. I think in the case where the proposal is to give up the fundamental postulate of statistical mechanics to give up probability, I think there that danger is very clear, right? Because once you have primitive non-identity, and once you say, oh, let's have 4 possible states instead of 3, what stops us from saying, oh, well, why not have 300 states instead of right? But I fear that this danger of non-identity might extend itself also to the coherent, right? Because if we say something like, well, if they might be individuals of a specific kind where they're mutually dependent, why can't we say, well, there are actually 300 individuals that are of a specific kind that are mutually dependent. They just so happen to be dependent, right? I think this is sort of like danger that comes up when we accept like primitive non-identity. But what would stop a coherentist from saying that we have 300 instead of 4 possible, instead of 3 possible combinations?
I'm not sure I see the analogy. I mean, in the quantum statistics case, one of the problems is that you actually decide beforehand what you want to obtain. So it has to be 4 states. So let me calibrate probabilities in the right way. And then I think you're right. I mean, if you want to calibrate, you will always be able to calibrate or whatever crazy idea you want to defend. And being able to stick to classical mechanics, to classical word picture is not necessarily a good idea. I agree with you. The point there is that there is nothing else outside of calibration because empirical evidence is there. And really, the statistics is that you have 3 states. Then, of course, we can discuss this. I concluded that, I mean, if you're a philosopher and you're really enthusiastic enough about dropping the fundamental postulate, we will insist on it. But anyway, in the case of coherence, things are different because I'm not calibrating my ontology to have classical ontology. I'm doing the opposite. I'm just looking at the evidence, and the evidence is telling me you only have things in symmetric states. And in this particular symmetric state, which is the state, which is paradigmatic quantum mechanics, the singlet state, really it is the physics that tells you that some values are ruled out. So in that case, it seems to me, but of course, it's all subjective. There is nothing artificial. I'm just saying, classically, you would see this. Quantum mechanically, you see this other thing. You don't see identities disappearing. You see some properties failing to be exemplified. So I'm not saying it's right. It is at least as compelling as something different. But of course, it depends on what one feels like more compelling, more urgent. That was exactly my.
Just a quick follow-up, sorry, Matt. So the idea is that you have already had independent ways of to go identities, and this is why it makes sense to count them this way. I'm just rephrasing.
Yeah.
That's what I would say, and I would agree with you.
well, if you have independent reasons, it's always a good thing, but maybe these are the basic reasons to actually think of a coherent ontology in the first place.
More than, well, the single state. So you start with single state, and then you reread the statistics.
Well, for me, I mean, this was the starting point. Of course, then you need to build a more comprehensive, encompassing ontology, and coherentism can give you that. There are a bunch of cases in the literature about mutual interdependence, symmetric dependence, reflexive dependence, which is basically to question the traditional view of grounding and dependence as, a partial order. And if we go along that route, there is a bunch of different things we might do. In this particular case, I'm focusing on the singlet state, but it's not just that. You have to be coherent. This means that you will explain singlet states in that way.
Yeah, I'll get back to this one again. Right. Mark.
Yeah, thanks. Very interesting too. Like my question is on 2P, in the sense that I don't see why you need recombination. Like it seems a bit too strong to require this additional assumption, because I feel like the way I understand the term is that like once you have like permutation invariance, then you already have like a way to like switch the individuals, and that's what gives rise. That's what gives rise to the whole Haecceitism problem. So like I think like free community is a bit too strong in the sense like if you just allow like once be able to switch the team, that's enough to give rise to the problem. Like permutation invariance is enough because like you don't need to be able to like freely recombine it, you can have like constraint. So
We're not exactly sure why this question is about 2B.
Because like you say like, oh, you need 2B to apply the argument.
Right.
And
okay.
I think like you don't actually need 2B, like 2B is not too strong. You just need to be able to switch the individual one.
Okay.
So you don't need like have like the full voice of the community.
Okay, let me thank you. This is useful because it allows me to actually be clearer on the way in which I structure the presentation. I mean, the argument that I started with was supposed to be the argument for non-individuality, right? So I was trying to do a service to my opponent in a way. And the idea is that if you want to conclude that if they were individuals, you would see this, you don't see this, then they are not. You need to make all the things that are doing some work explicit. They have to be explicit. And if you don't, and it seems to me, if you don't also add free recombinability, permutation invariance is not enough.
But why? I mean, I guess
because permutation invariance is just an empirical fact. In itself, it's nothing metaphysical, it's just something we see. It's a fact. There are no states which are only different with respect to labels. Okay? But this in itself cannot be sufficient for a metaphysical conclusion. Okay, if you don't agree with this, then you seem to be a radical naturalist, and I don't think I can say anything. But really, I mean, the evidence is never sufficient for a metaphysical conclusion. In this particular case, permutation invariance is just something we want to explain. And there are different ways of explaining it. If you want to say, well, look, there is one option which is not on the table, you have to explain that it is the following option: individual objects with monadic properties and free recombinability. Because in that case, you should have Haecceitistic difference. Now it's a normative claim. It's like an impossibility not to have them. Given that you don't have them, then you have a problem. This is connected to my first step. In the first step, we only have they may give rise to Haecceitistic difference, but they don't, which is the usual argument. But it's a wrong argument. If they may and they don't, who cares?
But yeah, so I guess like if
Yeah, very quick.
I guess like my argument about 2B comes from the way, I mean, like thinking about like space-time points, so the other case, like, you don't seem to have a problem with that.
No.
Because I need to come up. So it's like, I mean, it doesn't matter if you have it or if you don't have it. In that.
But you don't need to drop recombinability across the board. It depends on what you're describing. That's exactly my point. It might be that, considering all the cost and benefit, in this particular case, dropping free recombinability could be better than just coming up with a new ontological category, non-individuals. What are they? I'm not saying it's correct. I see your point. It's a cost-benefit analysis.
Yeah, that was a follow-up, sorry, follow-up or new question? You, yeah, sorry, you're new.
I have a new question.
New question. Okay, so I got 3, 4, you're 4, you are 5, 6, and then I have 2 questions. 3.
Thank you for the question. Super interesting. I actually have a clarificatory question because it seems to me that you're dealing with this debate, individuality of particles, and then your solution is just appealing to entanglement relations, right? Is this correct? Because you're not appealing to the ontological dependence between these particles. So that's why you go coherent in this case.
No.
And I'm just curious whether it's just about entanglement or not.
Okay, 2 sub-answers. The first one is, sure, the problem has to do with single states and doublet states, the finely quantum states. The other ones are similar to the classical states, and nobody complains about those. So obviously, if you want to make sense of quantum ontology, you need to focus on the specific quantum phenomena. Some phenomena in the microscopic domain are classical phenomena. Whenever you don't have identical particles, they behave according to classical statistics, sort of. Second point, no, I'm not using relations. Coherentists do not posit relations. That's the thing. If you're a structuralist, you would say, well, out there are a bunch of physical relations, and the world is probably fundamentally constituted by entanglement relations. Some people defended this in recent literature. It is viable. But I'm saying something else. I tried to. Well, I had it. Okay. This. It was quick, I know, but I was trying to suggest exactly where coherentists and structuralism differ. In my reconstruction, there is no mention of relations. I have 2 things with monadic dispositional properties and the composite system with a monadic total spin 0. There are no relations. Obviously, symmetric dependence relations are relations, but they are not physical relations. They are at the meta level. I'm just saying there are constraints on the way in which monadic physical properties are exemplified. So this is important for me because it's not structuralism, it's something completely different.
Follow up on this.
Yeah.
But structuralists may consider relations, but they consider also like laws or constraints or something else. So yeah, so in this case, why
again, I'm not saying that's not a way to go. I'm just saying, let's add this. Why? Because if you're a structuralist, the whole point is deflating intrinsic facts. Whatever is intrinsic becomes relational, right? That's the whole project. And I'm saying, if it comes to explaining entanglement, you can do it this other way. Stick to intrinsic identity if you want to. Stick to monadic properties if you want to. The evidence can be explained in terms of metaphysical dependence relations instead of changing your ontology at the physical level. And then again, it's a cost-benefit analysis. I'm not saying this is the way to go. Actually, I like it and nobody else does. So, well, a couple of people do. But yeah, that's not my point. If you don't like it, forget it. I mean, what is the argument? That's the big question.
4. You should know.
I have a question. I think it's more about like Haecceitism and the whole thing. From my understanding, maybe like my first assumption is wrong, so that's no question. So it allows the possibility in which we have two different qualitatively identical words, but which have achaistically, but which are achaistically different. We can say that they allow this, achaism allows this type of scenario.
You mean in general for
Yeah,
why
yeah,
it be?
but, I mean, like the idea is, if this is the case, I don't really see the point why, because it seems to me we have achaistic differences, like from achaistic differences, which is for example, like we exchange the two particles,
Yeah.
the particles, then we have a word which is qualitatively identical because this is what I'm saying. But it is still achaistically different, right? So I'm saying it looks like it doesn't really, it's not the argument against achaism.
No, I didn't want to provide one. I mean,
No, I don't see why this is a problem for achaism.
okay, maybe there is a missing element. The argument is based on the idea that statistical models, statistical arrangements can be conceived of as possible worlds. So purely statistic differences of the sort, this coin might have been another coin in China. That's not relevant. Let's stick to some specific possible worlds. The ones modeled, which seem to be modeled by quantum statistics, right? And quantum statistics seems to describe a world in which you don't have statistic differences. So you're not allowed to switch if you're not in a classical setting, right? Then of course, in a naive, innocent way, you might be able to say, well, whatever you describe, you can still switch. But that's purely superfluous switch. It's not statistically relevant. If you stick to those particular cases, then you need to have an explanation for what you see.
Yes,
No,
so the idea is achaistic differences should also should yield also statistics different, like statistical
exactly.
Okay. And some but statistical difference need not be qualitative difference.
That's the point. In the classical case, they are not. In the quantum case, there seems to be a correspondence between qualities and identities due to the fact that all the states are symmetric. In a situation in which you have symmetry, then you also have permutation invariance. I'm considering this, but there is a further step from symmetry to non-individuality. That was my point. So the identification I'm suggesting, well, not only me, is between existing differences and the failure of permutation invariance. If you have permutation invariance in statistics, then the analogy starts, and you can use your possible worlds philosophy to do some things here. But to a limited extent, not all combinations become relevant.
5.
Yeah, what I'm wondering is, all these different replies are attempts to reestablish that quantum particles are individuals. But why would we want that? What's the motivation behind it? Why wouldn't we just bite the bullet and say, okay, quantum particles are like the glass of water and the jug of water. They just don't have.
Well, let's start from scratch. Suppose you don't know anything about quantum mechanics, and people tell you, look, we have particles, and they are described by a different people. Then doesn't your mind go to something like tiny world in which you have small balls doing things and bouncing off each other, which is not necessarily correct. But our intuition is that things, if they are things, they are individuals. It's not like, well, we are indifferent. Some things are individual, some things are not. There is something, we come from some place, right? It's not like everything is purely neutral. I'm not saying this is an argument for individuals. It is an argument for asking the question. And I'm surprised by people saying, well, look, physics tells you clearly that they are not individual. I'm not saying they are wrong, it could be, but let me see the argument first. It's like saying, you know, relativity tells you that time doesn't flow. Right? The future is like the past. We all know that. It's probably true, but you know, it's not obvious that it's not an it's a cause, right? It's not just bad because it's a cause. You know, sometimes we need to drop and trench to this. I'm fine with that, but we need to have clear, compelling argument for doing it. That's my point.
Wouldn't the argument, the primary argument here be a clear and compelling argument for dropping and then trench beliefs that there are individual?
Well, I try to be clear that none of these arguments, including mine, are conclusive.
Yeah.
Whether they are compelling, it's really subjective. That was my last point. I cannot tell you that my proposal is better because I don't have any measure of being better philosophically. Unfortunately, I'm just telling you, look, these are the options. Maybe there are others. It's your job as philosopher to think about them and think about the arguments and see whether you see flaws, whether you see alternatives. I think it's very, I mean, we should stop saying, well, look, if you are naturalists enough, we will learn from science that things are like this, you know. Presentists are wrong, the flow of time is an illusion. It could be, but before we go that route, we need to be careful.
Yeah.
Our job is to be sharp and to be precise about formulating the arguments and seeing whether there might not be objections, whether you can attack the premises. It's a very basic point.
Yes.
Thank you. I'm not in speed, but behind the new option, the idea is this one. We cannot have just merely probability, but we have conditional probability. So under certain assumption, and these are the mutual. This is the mutual dependence. So under this condition, we have.
Yeah, I mean, in a way, it's like this. It's not directly a point about probabilities, but you can formulate it this way. If you look at the probability assignments for different properties assignments to independent individuals, and then you have this interaction leading you to entanglement, entangled system, then probabilities change. So conditionally on the interaction and on entanglement arising, you change the probability assignments for the relevant properties. And I take this as an indicator that something is going on at the level of, you know, we used to be independent and now we interacted and now we have to pay attention to each other. Because if it does spin up, I have to be careful and do spin down. Otherwise, we violate the exclusion principle. And it is mirrored in the probabilities, but it's not immediately a point about probability.
So go to the people online. I didn't label that, so people online.
There is no right level.
Can I help you?
Oh, there is people, but I let Carol ask the question first.
No.
I guess you were first.
Hello?
Can you hear me?
Yeah, I can hear you. Can you hear me?
Yes.
Yeah.
Yeah.
Yeah, okay, so I can go ahead or Carol
go.
ask,
Go ahead.
Yeah, okay. My question is the following. I'm perplexed, honestly, because if I take, you already move from the assumption that particles as such have individuality. But I mean, if you take a vacuum, and with a wave function in there, as complex as it is, where is the individuality? There is no individuality. The individuality starts when you make a measurement, and then you can start labeling, so to speak, particles. But before that, there is no individuality, if you follow me.
Yeah, I agree with you.
You already moved from a de facto situation in which there is individuality. And of course, when you make a measurement and when you start labeling particles and you put them not in a regular space-time continuum, but rather in a phase space, and then of course all your particles are labeled and you can start switching them and they have property, and then your reasoning starts from there and follows smoothness, because otherwise the big question would be, how can you get the individuality at macro level if you don't get the individuality sooner at a micro level? So, but the big question is, for me, it would be, okay, well, where does this individuality comes? And in my view, the individuality comes in the moment in which you make a measurement taken in the bigger sense, meaning that you start interacting with your system. If there is no interaction, the wave function won't collapse and there is no individuality. That's the point I wanted to make. Yeah.
I agree with you. I mean, it is a big question whether quantum mechanics is describing objects at all. If we're realist about the wave function, of course, the question is moot. The point is different, though. I mean, I think it's really wise in philosophy to make the same assumptions as the people you want to discuss. And the assumptions that I made are the assumptions that are made in the literature. Supposing that you're working with non-relativistic quantum mechanics and the labels are actually labels of something, which is a big if, then the usual argument is these things being labeled are objects, but they are not individuals. And the argument follows. And I'm saying, look, making the same assumptions, I notice that the conclusions don't follow unless you add some more assumptions. So it's all conditional. I agree with you. I'm not saying that my conclusion was, and therefore the world is made of small individuals. I was clear about this from the outset. I don't know what the world is made of. I'm just saying, well, look, let's do something more modest. Pick an argument in the literature, pick the received view, pick the way people usually think about your domain of study, and see whether there is really an argument there. So in a way, I'm going towards your direction. If there is no argument, then we can start asking other questions.
Yeah, I fully agree with you. As I said, it was not a criticism, it was just a remark, because if one starts saying, well, particles, well, there is no individuality at quantum level, non-relativistic, relativist, it doesn't really matter, then where does the individuality come from? Because me and you are not the same individual. So this individuality has to come from somewhere. And so if one maintains a position that there is no individuality at micro level, then one has to say, it has to explain me, where does this individuality come from? Yeah, that was just my remark, but thank you. I think it was very, very interesting. I had some problem here in the audio at the beginning. The quality was not that brilliant, but thanks for the slide. And I was just wondering whether you are going to share the slide deck.
Yeah, sure. Why not?
Yep. Okay. Cheers. Appreciate.
Thank you.
Thank you very much.
How much time do we have? Because no. So it's 1 hour 30 overall. Yeah. Okay. We started 5 days, so we can get the last question from Carol online. Sorry if I misspelled your name.
Yeah, it's everything perfect. Can you hear me?
Yeah.
Okay, thank you. So 2 really quick points about combinatorialism. So the first one, in your argument, I'm not sure that in the argument that you have reconstructed, you assumed strong combinatorial principle, that Humeanism, and I think that maybe it is too strong. Maybe the argument will work on a weaker combinatorialism, saying that two particles of the same kind can swap their qualitative profiles. Maybe we don't need in this argument to say or to assume that anything could swap a qualitative profile with anything. So this is the first point. And second one, if we assume this strong combinatorialism, as you did in your reconstruction, then you provide a counter-argument to this. And your counter-argument, I guess, is a nomological argument that you appeal to some nomological necessity. And I worry that this might not undermine a metaphysical thesis of combinatorialism, because Humean could say, but in other worlds, there are other laws of nature, and then your argument only applies to some particular worlds with a particular laws of nature, but in other worlds with other laws of nature, your constraint of ontological dependence doesn't work, and so yeah, those are my two arguments. Two points.
Yeah, the first point, thank you. I agree with you. We wouldn't need a reason for actually subscribing free recombinability only in a specific domain, I think. So it's not necessarily an advantage. But your point is fair. As for the second point, I'm not really sure that we should really put so much weight on worlds in which the laws of nature are different and Hume, Armstrong, and Lewis are right. You know, we care about quantum mechanics, which is a theory about the actual world. I'm not saying that it's necessarily the case that every physically possible world, metaphysically possible world has to be quantum mechanical. But my aim was to provide an explanation of what is contingently, what seems to be contingently the case in the actual world. And I'm pretty convinced that in the actual world, the human perspective is really weak. But I'm not saying that it doesn't work. I mean, it's not contradictory, of course.
Okay, I see that you limit your attention to worlds with quantum mechanical laws that are actual, and we focus on that. Okay.